Hello everyone. So in the previous videos, we already saw binary exponentiation and Fibonacci numbers. And in this video, we will see Sieve of Eratosthenes, which is used to find prime numbers from 1 to n. Now, let's quickly recap what is a prime number. Prime number is a number which is divisible by 1 and itself. Let's suppose x is a number, so it should be divisible by only 1 and x. Right? Now, one way to check whether a given number x is a prime or not, you just iterate from 2 to x 2 to root x, and if let's say that the current number is I, and if x modulo I equals to 0, then you return false because it is divisible by I, which is not equals to 1 or x. So in this case, x is not a prime number, otherwise you return true. Now, if I give you, if I tell you to find all the prime numbers from 1 to n, you can't run this algorithm because it will take n approximately n root n time complexity, because for every number you have to run a root n algorithm. Now, how to do it quickly? So here comes the Sieve of Eratosthenes algorithm, which say that you uh, first mark 1 as false because it is not a prime number. So and 2 as true. Right? You don't have to do this. Mark 2 as a true. First, maintain a vector of length n and mark the first number as 0 and other number as or false and other number as true. Now start from 2, and you know that all the multiple of 2 is not a prime number, so you iterate over all the multiple of 2, that is 4, 6, 8, 10, and mark it false. So you mark it false, you mark 6 as false. Now you come to 3. You will first check whether 3 is already marked as false or not. If it is already marked as false, means it is not a prime number, because some number less than 3 already uh, divides 3. So, we skip in that case. Otherwise, if uh, it is marked as true, then if 3 is a prime number, and what you have to do, you have to mark all the multiples of 3 as false. So you will mark 6, 9, 12 as false, right? So let me show you this. This will make it clear. I do just make a array 2 to 16. Initially, all are true, right? Now we start with 2. Start with 2, and you will mark all multiple of 2, that is 4, 6, 8. You will cross this. This is not a prime number. Now you will come to 3. You will check, oh, 3 is not marked as false, so you will go to multiple of 3 and you mark it false. You cube, and when you come to 4, you will see that, oh, it is already marked. Then you skip this and you come to 5. So 5 is marked as true, so 5 is a prime number. Now you go to multiple of 5. 10 marked as false, 15 marked as false. If you keep doing this, and the finally whichever uh, array element is marked as true is your prime number. Now let me show you the code, then I will prove the time complexity. So here is the code. You first maintain a array is prime, and this is a C, and I want to calculate prime number up to size. So I am marking 0 and 1 as false. Now I am iterating from 2 to size, and if it is uh, true, means it is a prime number, then I am iterating over its multiple and I am marking it as false. Now, why I am not iterating from 2 into I? Why I am iterating from I into I? Because Let's suppose you iterate from j equals to 2 multiplied by I, and you go up to size, and you are doing j plus equals to I. Uh, you don't have to do this. You can start from I into I, because uh, you know that this number, that you know that one of the multiple is I, and if the other number is, let's suppose g, and if d is less than I, then this is already marked by d, right? Let's suppose I am at 3, and I am starting from 3 into 2 means 6. But you know that when you are at 2, then you have already marked 6. 2 into 3, which is 6. So you have to start from I into I, which save your complexity also. Now let's prove how uh, uh, the complexity is analog of log n. So first see that for each I, you are going up to size, right? So for each I from 2 to n, you are going n by I. You are doing n by I iteration, right? Roughly. So take n out and summation 1 upon I, which is indeed log n and log n. But uh, when you see this, then when you dive deeper, then you will find that you are doing this only for prime number, right? Now, how many? Here you see that if it is not prime number, you are skipping that iteration, right? So first you notice that uh, there is a property, or it's roughly mentioned that from 1 to n there are n upon log n prime numbers approximately. So how many times you are doing this iteration? N upon log n times. And you are telling that means the kth prime number is k log k. This is our approximation to prove the time complexity, right? K log k. So you can rewrite this summation as summation uh, from n upon log n I equals to 1 to n upon log n I log I, right? And when you sum it up, you will get n log of log n. I'm just giving you a feel why it is less than n log n. So this proof is not really necessary. You have to remember the algorithm to solve the problems, right? Now, uh, before doing questions on C, we will let's see some variation of C. Let's suppose you have to find all the prime numbers from L to R. You can simply say that I will find a prime number up to 1 to R, and I will see all the prime numbers from L to R, right? But the constraint is that L and R can be up to 10 raised to power 12, but R minus L plus 1 is less than 10 raised to power 5. This is given to you. Means the length is up to 10 raised to power 5, but the L and R is very weak. You can't just find prime numbers from 1 to R and take out the all the prime number from L to R. Means you can't find prime number from 1 to R and then take the prime number from L to R, right? Now, for this, what you can do is basically first find all the prime numbers up to root R. Means find all the prime numbers from 1 to root R, and then remove all the composite number from L to R. I will tell you why I am doing this. So, how to remove maintain a vector L2R. Right? You will convert it to zero indexing and look at all the prime numbers from 1 to root r. Iterate over all the prime numbers from L to root r and mark all the multiple of p as false. And finally, what you will get, all the numbers, all the elements that is marked as true is your prime numbers. First, let me show you the code. So segmented C, you have to find L2R prime number up to uh, L2R. Now you first generate all prime number up to square root of R. So this is simple as C. You are generating all the prime numbers up to L2R, and then you are storing it in a vector primes. Now you iterate over all the primes and you go to the multiple of I, j equals to I multiplied by I, and this is basically finding uh, the multiple of I which is just greater than or equal to L, and you are going up to R and you are adding I, and you are marking that element as false, and uh, if L equals to 1 then obviously it is false, and this array is basically contains the required result, means all the element which is marked as true is prime and others are composite. Here you have to generate up to root r only, because uh, if you let's suppose go up to root r plus 2, then in that case root r into root r plus 2 will exceed r, so you will not get any element in this range, right? Because you are starting from I into I, so it will already exceed r, so you only need up to r, up to root r prime numbers. In the next video we will see some application on Sieve. We will do some problems, and also if you have any doubt or any feedback you can comment. Thank you.